Hello, this video lecture is meant to explore the concepts found in Unit 10.5 on colligative properties. We need to begin by recognizing that there's some reference tables that will be useful to you, so I want to make sure that you know exactly where to find them. So reference table B, specifically we are looking for the boiling point elevation constant and the freezing point depression constant. So we're not going to say anything about them just yet, just recognizing that you'll need to know where those are. And then on reference table T, down here at the bottom, you can see that there's colligative properties. And again, we'll talk about these, but recognizing that those equations are there for you to utilize. All right, this is the cover sheet from Unit 10.5, which summarizes the unit, and we'll sort of use this as our springboard to kind of understand the different concepts. Starting with point number 20, this is trying to tell you that the more concentrated a solution is, the more solute that you have added to solution, there's an effect on the solvent's vapor pressure, the boiling point, and the freezing point. Now, these are all colligative properties, and colligative properties, the strict definition of this is that these are properties that are dependent on the number of particles dissolved in solution. These properties, boiling point and freezing point, do not depend on the identity or the properties of the particles, only the number of the particles. All right, so that's what we're going to be studying, is the effect on the boiling point and the freezing point. All right, so we're actually going to begin by talking about what we talked about in 10.3, this unit of concentration, which is called molality. Molality, as you might recall, was when you have the number of moles of solute divided by the kilograms of solvent. And this particular unit of concentration, the big difference between this one and the other concentration units is that the denominator is all about the solvent. Because when you are talking about the changes in boiling point and the changes in freezing point, we're talking about the change in the freezing point of the solvent, the water. We're talking about changes in boiling point of the solvent, the water. So we need to have a unit of concentration that's all about based on the mass of the solvent, not based on the solution. So that's what we're going to be using as our unit of concentration when we do our colligative property calculations. Now, we're going to skip number 21 just for a second to talk about 22 and 23. The boiling point of water is going to go higher than 100 degrees Celsius whenever you dissolve something into the water. And it's a very quantitative relationship by how much that boiling point will increase. It is for every 1 molal solution, the boiling point is going to go up by 0.52 degrees Celsius. So this is this is a constant. The boiling point elevation constant is equal to, it's a positive 0.52 degrees Celsius per every 1 molal of solution. And again, that can be found in reference table B, which I showed you a moment ago. The freezing point of water does just the opposite. It pushes the freezing point lower than 0 degrees Celsius. Quantitatively, for every 1 molal of solution, the freezing point will go down by 1.86 degrees Celsius. So this is called the freezing point depression constant, and it is equal to negative 1.86 degrees Celsius per 1 molal. Now, putting that together, going back up to question number 20, or not question, but point number 21, I'm going to actually bring us down here to take a look at it. The quantitative effect a solution has on the change of the boiling point and the change of the freezing point is represented by these two equations. So delta TF is equal to I, we'll talk about that in a minute, times KF times M. So we know what M is. M is the molality of the solution. We know what KF is. That's the freezing point depression constant of negative 1.86 degrees Celsius per every 1 molal solution. I is going to refer to the number of particles that the compound dissociates into. We'll talk about that in a moment. But when you multiply those three numbers, it is equal to delta TF, which is said to be the change in the freezing point temperature. Okay, so that's what that is going to help you calculate. The other equation is delta TB, which is equal to I times KB times M. And so delta TB is the change in the boiling point temperature. Okay. All right, next point. We have to talk about this I factor. Number 25 and number 26 is talking about how you figure out the I factor. 25, if the solute is molecular, meaning it's a covalently bonded compound, and again, you're recognizing this because you're looking for all metal elements in the compound, that's going to be considered a non-electrolyte, and it will not dissociate. What that means is that a non-electrolyte compound cannot break apart into ions. It stays together as a single unit, and so the I value is going to be equal to 1 for any non-electrolyte. So all you have to do is recognize that a substance is molecular, all nonmetals in the compound, and you know the I factor is going to be 1. Now, if the solute is ionic, it is considered to be an electrolyte, and it will dissociate. The I factor is going to depend on the number of ions the compound dissociates into. And so that requires a little bit of practice. You have to be able to look at a chemical formula and be able to kind of break it apart and see how many ions went into making that compound. We'll get a practice with that in the problem set. Looking at the problem set, just going to give you a quick little tour about what's going on in here. Part A, you are going to be calculating the molality of the following solutions. Remember, molality is equal to the moles of solute divided by the kilograms of solvent. Part B, you're trying to write the dissociation reactions, and I'm going to make this bigger so we can see this a little bit, so that you can figure out the number of ions. The number of ions basically is going to be your I factor. Wanted you to also recognize that the I factor is also sometimes known as the Vant Hoff factor. You're going to see that in your vocabulary, that the Vant Hoff factor is the number of ions that a substance dissociates into. You may also find that table F can be your friend, not table F, I'm sorry, table E, the polyatomic ions. To be able to recognize the polyatomic ions, table E can be your friend. So for example, the first one, KHCO3, you might recognize CO3 as carbonate, but if you only choose carbonate, then K and H are kind of left out in the cold here. So really, HCO3 is written because HCO3 is hydrogen carbonate on reference table E, and then this makes a little more sense because then potassium is the cation here. So this one would have an I factor of 2. All right, and so this substance would have twice the impact. It would double the increase in the boiling point, and it will double the impact of the freezing point. Because you'll be multiplying by 2 in those equations. So the more a compound dissociates, the greater impact it's going to have on the new freezing point and the new melting point, and the new boiling point. Okay, so that's what you're doing in B. In part C, you've got these compounds listed here. You have to decide if they're ionic or molecular. Remembering ionic, you're looking for a metal and a nonmetal. For molecular, you're looking for all nonmetals. Okay. If it is molecular, it's a non-electrolyte. If it's ionic, it's an electrolyte. It's that simple and straightforward. If it is a non-electrolyte, the I factor will always be 1. If it's and that's what you're going to put in this column. If it's an electrolyte, you're going to have to figure out how many ions it dissociates into, and then that will be your I factor. And then the last column, you have to decide the impact. You're going to rank these 1 to 4. 1 is what you are ranking as the least impact, and 4 is what you're ranking as the most impact. That seems a little backwards, but that's just how this is set up. On the second page of the problem set, The multiple choice here is going to give you a chance to answer some, these are kind of conceptual problems with the new boiling points and the new freezing points. And then part E, this is where you're going to do some quantitative work, where you're going to be using the delta T B is equal to I KB times M, and the delta TF, where you'll be using I KF M. So that's where you'll be calculating those new temperatures. All right. Best thing to remember is that once you have the delta TB, you have to add that to 100 degrees Celsius. And once you get the delta TF, you have to make sure that that number goes, you have to subtract that from 0. So 0 minus that number, because it's going to be a temperature lower than 0 degrees Celsius. All right. That gives you hopefully a good overview of what this unit's about. Have a good day, and we'll see you in the classroom.